This class, we have seen other types of systems which are possible in one-dimensional conduction conditions. First one which we have seen before CAT is lump system. And yesterday I have drawn a temperature profile of a lump system. The lump system temperature will look at different time steps and how a distributed system's temperature will look at different time steps. So you must have understood now that in a lump system, thermal gradients are not existent or extremely minimal, whereas in a distributed system, the thermal gradients are considerable and therefore can use the conduction equation. And we have also seen some solutions, some equations which are obtained as solutions for the two distributed systems. The first distributed system is the infinite body, and the second one is the semi-infinite body. And also, I have told you a few thumb rules to identify whether a system is lumped or infinite or semi-infinite. But for all these transient systems, first from the problem statement, you should be able to understand whether it is a steady state system or a transient system. If the system is steady state, whether it is one dimensional or two dimensional, and accordingly you will have to take the approach. If it is a transient system, in your syllabus we only have one dimensional transient system, so no two dimensional transient systems will come into picture. But in one dimensional transient systems, as we have seen, there are three different types of bodies possible. So we should be able to identify which one, and to identify whether it is a lumped or distributed system, the first step is to calculate the Biot number. Okay, so that is mandatory for every problem in transient system. If your Biot number is less than 0.1, you are lucky. You can use the lump system equation, simple equations, and directly obtain the analytical result. Whereas if it is a distributed system, you will have to do another check. If it is a distributed system, then you will have to check whether the Fourier number is greater than 0.2 or not. Okay, so basically two things you need to calculate, Biot number as well as the Fourier number. If the Biot number is less than 0.1, good for you, lump system, you don't have to check the Fourier number. But if it is a Biot number greater than 0.1, then you will also have to check whether the Fourier number is greater than 0.2, and only then you can use either the one-term approximation solution or you can use the Heisler's charts and the Grover charts. Okay, so you'll have to keep all these things in mind. And as I always say, it comes with practice, so you will have to practice. So as a part of that practice, we'll also solve some problems in this class. So share my presentation. So this is one problem which we will take up today to solve. And since in the lesson, in the sequence of the lesson, we are in the infinite bodies, you can understand that this is a problem related to infinite bodies. But in a problem, in an exam like environment, you would not know which type of system this is. Then you will have to do all the necessary checks. Okay, so let me read the statement. An iron plate, conductivity, specific heat, density, and thermal diffusivity are all given. Of a 50 millimeter thickness is initially at 25 degrees Celsius. Suddenly, both surfaces are exposed to an ambient temperature of 25 degrees Celsius with a heat transfer coefficient of 500 watt per meter square Kelvin. Okay. Calculate the center temperature at 2 minutes after the start of the cooling. Then B, the temperature at a depth of 1 centimeter from the surface at 2 minutes after the start of cooling. Then the energy removed from the plate per unit area during this time. Energy removed means heat energy removed. In heat transfer, energy means only heat energy. Okay. So there's three questions. So basically you will have to find out some temperatures at certain times. So this is the typical nature of a transient problem. Time time will also get involved. So temperatures and heat transfers at different times and at some locations. This is what is specified. Okay. So we'll try to solve this problem. So we can see that this is an iron plate. So this is basically a plain wall kind of a problem. So you'll have to use the, the equations or the charts which are available for a plane wall and go ahead with the calculation. So as always, I insist that you will have to draw the schematic diagram. So schematic diagram always like this. This is a rectangular plate. So I will draw this rectangular plate. The thickness I am exaggerating is the plate and this is the center line. Let us call this as a cell. So if you look in your data book, all the plates or the equations or the charts available for these plates are in the form uh, of slabs having thickness 2L. Okay, so that is the reason why I have taken this as thickness of 2L. So each half is L. So we are given data 2L is L. Also, we are given some initial condition. Initial condition is 225 degrees Celsius temperature. High 5 degrees. Suddenly exposed, both surfaces are exposed to an ambient temperature of 25 degrees Celsius. The heat transfer coefficient 5, H is equal to 500. This side also T 500. But we are supposed to calculate the center temperature at 2 minutes after the start of cooling. So let us, I'll write it here. Center temperature at tau is equal to B, the temperature at a depth of 1 centimeter from the surface. Point. Let's write this depth from at the surface 2 minutes. Okay. Start of cooling and the energy removed. So basically for our problem, the time is tau is 2 is 120 seconds. Time given to us. So this is the data we have. Three questions asked. After 2 minutes, what is the center temperature? What is the temperature at a location of 1 centimeter depth? So you can see that this width of the plate is 50 millimeters. So half width is 25 millimeters. That is 2.5 centimeters and 1 centimeter depth. So if we say that this point is 1 centimeter deep, this distance will be 1.5 centimeters. This is 1.5 centimeter. This is 1 centimeter. So 2.5 centimeters somehow. So that is the millimeters converted to centimeters. Okay, so this is the problem. Now we'll have to solve the problem. First of all, we are told to find out what is the temperature after 2 minutes. So therefore, straightforward, this is a transient problem. Problem is transient problem. Transient conduction. Now the next check is we have to see whether the thing is biot it is lumped or not. So first step is always calculate the biot number. Biot number is hx by k. H is the heat transfer coefficient, x is the characteristic length, and k is the thermal conductivity. So we are given the value of h. H is 500. X is nothing but L. L is 25 millimeters. So 25 multiplied by 10 power minus 3 divided by the conductivity. We are given the is here. Conductivity is 6. So we'll have to calculate this value. You also calculate and tell me what is this value. How much is the Biot number?
0.208.
0.208, which is greater than 0.1. Therefore, the system is not lumped. Okay. So now the option available to us is whether it is infinite or semi-infinite. So now you can see that some of the data is given. This is a finite width of this plate, finite width of 50 millimeters. So this is most likely a infinite body. So we'll use the equations or the charts available for the infinite body. So if you look at the for the charts available for infinite plane wall. This is the infinite plane wall. You can also open your data books. In your data book, the page number 74. Page number 74 contains this one. Mid plane is in page 74 of the data book. Data book, my edition is the 9th edition. In page number 74, you will see this. Then you will see that. See, first the question to be answered is the center temperature. Center temperature means the mid plane temperature at 2 minutes after the start. So for that, you see, you have to use this chart, and for using this chart, I will have to find out what is the Fourier number and what is the Biot number. In this case, inverse Biot number. So we already have the Biot number, so we have to inverse it, and then we'll have to use it. If you are using the charts that you have in in your data book, in the charts in the data book, the x-axis is Fourier number and the y-axis is simply Biot number. Here it is inverse of Biot number. There in the data book, it is Biot number. But the ultimate result is still the same. So I will first demonstrate how to do this here, and then we'll go to the data book. First, we'll have to calculate the Fourier number. So you can see that the Fourier number. Remember, Fourier number is a non-dimensional time. So time will come into picture. So alpha tau by L square, or L here is x. So alpha tau by x square or L square, whatever it is. Okay. Now alpha is given in the problem to us. Alpha is 1.6 into 10 power. Time is 120 seconds. Divided by x is 55 into 10 power. Sorry. Okay. So calculate this value. 3.07. Fourier number is 3.07, and Biot number is we got 0.1, 0.208. 1 by Biot number is 4.8. So Fourier number is 3.07, 1 by Biot is 4.8. Now remember this. Fourier number is 3.0 and 1 by Biot number 4.8. Okay. Now 3.07 have 1 here, 2 here, 3 here, 4. So 3.07 is almost 3 or slightly to the right of 3. So this is let us here, and then we have 1 by Biot number as a 4.8. 4.8 is so you see here this is going somewhere in this region, and for our convenience this region is actually enlarged in this smaller inset. So this is to our advantage. So this is 3.07, and this is 3, this is 4, this is 5. So go up like this. So it is somewhere, this line has gone inclined. So somewhere between 0.5 and 0.5 and 0.6. Okay. So we'll also confirm this from the charts that from the Heisler chart that we have in the data book. Okay. In the data book, x-axis, the Fourier number is 3.07. It's almost 3, and Biot number is 0.21. Okay, we'll go by the data books for Heisler's chart. So 3 and 0.2. It is somewhere at about uh, 0.6. It's roughly 0.6. Okay. So this value is 0.6. That's what it is turning out to be approximately. Remember the Heisler chart, it depends on how accurately or how well you read and how well you interpret, because you cannot accurately point out each and every point on this chart. And each person will have his own different interpretation. So ultimately you will get only an approximate value. So you see here, the y-axis value is about 0.6. That is what you are getting in this. So this y-axis is basically this ratio, T naught divided by Ti, T naught minus T infinity divided by Ti minus T infinity. But from
So how do we read this chart?
sorry,
So how do we read this chart?
I just showed you how to read it. On the x-axis, locate Fourier number 3.07, right? So it's somewhere here. On the curves, you have 1 by Biot number. See this Biot number inverse, which is 1 by Biot number, is 4.8. So you have here 3, 4, 5. So it's somewhere between this one. So some straight line here, 4.8. It is going into this region, which is more clearly shown here. So in this inset picture, you can use, this is the Fourier number on the x-axis, and you want the parameter 1 by Biot number 4.8. So this is 3, this is 4, this is 5. So somewhere in between is this one. This is 4.8. So this vertical line from 3.07 and this 4.8 parametric line will meet here, and that you project onto the y-axis. This is somewhere
So, so
0.6.
Sir, in my data book, it's only the BART number and not 1 by BART.
That's what I'm saying. You use Biot number only. And tell me what's your y-axis value.
Point 208 or around
2.
0.2.
Yeah, so y-axis on the parameter, locate 0.208. You will have actual lines 0.1, 0.2, and 0.3. So somewhere in between 0.2 and 0.3, but closer to, closer to 0.2, you will have to draw an imaginary curve.
Okay, sir.
Now tell me what's the y-axis value.
So it's coming somewhere close to 0.8.
Now
Answer.
read accurately, it's not 0.8, it will be close to 0.6. It will be around 0. So from the Heisler's charts, I will draw it clearly here. You have Fourier number, you have Ti minus, T minus T infinity divided by Ti minus T. So this is T naught. T naught stands for the center line. And here we have some parametric curve. So from the Fourier axis, locate the Fourier value of 3.07, and this Biot number is 0.208. So on this, draw a vertical line here, and from this, draw a horizontal line here. So this value is supposed to be approximately 0.6. Okay. So this is how you need to locate. So now we have T naught minus T infinity divided by Ti minus T infinity is equal to 0.6. Now we have T infinity as 25 and Ti as T naught minus 25 divided by 225 minus 25 is equal to 0. So this implies T naught. T naught is the center temperature. So that will be 145 degrees Celsius. Okay. So this is the solution for part A. Therefore, center temperature is 145 degrees Celsius after 2 minutes. Okay. Everybody followed this? Are any questions? I'd like to pause here and see whether you are the same page or not. It's important that you keep your data books with you during the class. All right. Our next question is, find the temperature at a depth of 1 centimeter from the surface at 2 minutes after the start of cooling. So we have part B. So this is here to here, it is 0.5 centimeters. From this surface, let us say this is 1 centimeter. So this will be inputs. Okay. So we have to find the temperature uh, at this location of is at a depth of 1 centimeter from the surface or 1.5 centimeters from the mid plane. So Now you see here, this is the mid plane, and we are measuring the x in the x. So in our case, this case x is 1.5, L is 0.5. Therefore, x by L is 5. How much is that? 0 points. By L is 0. Now I want you to turn to page 75 of your data book, or I'll just take chart. Is the chart for a plane wall at any plane. So to find the temperature at any plane, see for mid plane there is a separate chart. This chart which we used just now. Now at any plane we will have to use this. So to use this, you see on the x-axis we have the Biot number, and the parametric curve is x by L. Okay, so we'll have to use this. What is our 1 by? So we have 2 here, 3 here, 4 somewhere between, somewhere close to 5, but before 5. So I will roughly mark this. Okay, and this is 0.6. This curve is 0.6. So I'll have to project a vertical line. Not able to draw this vertical lines. Yeah. So from here, draw a horizontal line onto the y-axis. So this value is somewhere above point, somewhere between 0.9 and 1. Can say this value is probably 0.95, from roughly between 0.9 and 1. If you draw accurately, you may get it. You also have your data books. In your data books, page number 75. In page number 75, instead of on the x-axis, instead of 1 by Biot number, you have Biot number itself. Your Biot number is 0.208. So locate 0.0208 on your x-axis and the parametric curve on the y-axis, and you can see that they meet at about 0.95 or little above 0.95 actually. Okay. So the Heisler chart here, Biot number, and this IL is and Biot number is here. So you draw a vertical. This will be, what is this value? Tx by L minus T divided by T naught. T naught is the center temperature minus T. This value turns out to be approximately point. So from this we'll have to find out Tx by L minus T infinity is 25 divided by center temperature. We found 5. This is therefore Tx by L. X by L at 0.6 equal to 139 degrees Celsius. So what we got here, you see, at the center, the temperature was 145, and at a depth slightly away from the center, the temperature is 139 degrees Celsius. So if you try to plot the, the temperature distribution after 2 minutes, you'll see that this is the mid plane. Center temperature is 145, and this temperature is 139, something like this. This is at tau is equal to. Okay. Is this clear? This kind of chart solutions we'll be using often in transient conduction. This is where the next type of model, uh, solid model, is a semi-infinite. For that also we'll be using a similar charts. Okay, so try to follow. If you have any questions, you please ask. See, in some case, in the chart that I am showing you, which I have taken from a textbook, this the chart by Biot number here. So saying 1 by Biot number, but in the data book you have simply the Biot number. But accordingly, these curves are changed. So you don't have to worry whether you're looking at the right chart or not. All the charts are right, whether it's a Biot number or 1 by Biot number. No problem. Don't hesitate. Go ahead and use it. Okay. Now the next question: the energy. The heat energy removed from the plate per unit area during this time. So what is the heat lost? Okay. So for that, you see here you have to use the Grover chart. So in the Grover chart, you have on the x-axis you have Biot square multiplied by Fourier. So we now have the Biot number, Fourier number also, and it's the same time, 2 minutes only. So the same Fourier number can be used. So Biot square Fourier number can be calculated. Then we have on this, the parameter is Biot. Biot we already have it. So using the x-axis value and this parametric curve values, we can identify a point, and if you project that point onto the y-axis, you will get a value of Q divided by Q naught. So what is this Q? Q is the heat that we are supposed to find out. What is Q naught? Q naught is the data book. Let us see how this Q naught is described. Q naught is the heat capacity of the body above T infinity for a unit area. Okay. For a plate, it is rho Cl multiplied by Ti minus T infinity. So it's nothing but basically the maximum possible heat transfer. It's like mCp delta T at T is equal to, at tau is equal to 0. mCp delta T. So that means mass of the plate multiplied by the specific heat of the plate multiplied by the temperature difference. That is initial temperature difference. So the initial temperature of the plate minus the convection environment temperature. These both things, if you subtract, then you will get the maximum possible heat transfer. So this particular Q by Q naught, Q by Q naught is basically a fraction. You can see on the y-axis, it varies from 0 to 1. It's a fraction. So actual heat transfer divided by the maximum possible heat transfer. So you'll get a fraction. If you can calculate the maximum possible heat transfer, you can calculate the actual heat transfer. So we'll calculate what is Q naught. Heat here. Q naught is simply mCp multiplied by delta T at tau is equal to 0. That the initial thing. Initially, the temperature difference between the object and the convective environment is maximum. So that gives us the maximum heat transfer that is possible. So mass is density multiplied by the volume, and Cp and delta T. Tau is equal to 0. Okay. Now We are given the density in the problem. The density is 7,850 and the CP is 0.46 kilojoule per kg Kelvin. 7850 density multiplied the volume. Now, what is the volume? Volume is area into thickness. So let us say area, I'll write it here. Volume is area multiplied by 2L. Area will take unit area multiplied by, so this is multiplied by 1 divided by 50 10 power minus 3. 3 millimeters is the thickness. So this is the volume. Volume multiplied by the density will give you the mass. So this is the multiplied by the Cp is given as a 0.46. But remember, this is in kilojoule per kilogram Kelvin. Therefore, whatever heat you calculate here, that will also be in kilojoules. Multiplied by the initial temperature difference. So this is 225 minus. Calculate this value. This is 36,110 kilojoules. So this is the maximum possible heat transfer. Okay, now let us go back to the charts. But from the charts, we have seen that you will need to use the Grover charts. You will need bio and Fourier number, bio square multiplied by Fourier number. What was the 0.208 and Fourier number 3. 0.13. So this is what we have on the uh, axis, and the parameter is Biot number. Biot number is 0.208. So remember this. So on the Grover charts, we'll have to get Bio square for here is, and then the Biot number is given parameter from value of. Now we'll do that. Biot square Fourier is 0.1328 and Biot number is 0.208. 0.1328. Now this is 0.1 and this is 1. Somewhere 0.1328 and 0.208. See, this is 0.2 line and this 0.5 line. So somewhere in between. What is here? So have in the part, this is 0.1. Read this carefully and accurately. Get somewhere close to 0.5, but slightly, but 10.5. I am getting on this chart between 0.4 and 0. This is do it accurately. Use a scale. Always use a scale and a pencil so that you get these things accurately. So as of now, Q by Q naught, I'm taking it so Q is 0.45 multiplied by 0.13 as Q naught, 36,000. So 16,240. Is it joules or kilojoules?
So kilojoules.
Kilojoules. Because our CP was in kilojoules. 16,240 or simply 16.2 megajoules. Write it like this. So this is the way in which you will have to proceed. Obviously, you are reading from charts. Therefore, no two students will have the same result. You will have to manage. But if you want to get a realistic value, more correct value, then the best way is to use the equation. You see here, this equation, temperature distribution in an infinite plate. You will have to use this equation to find the temperature at be it the center or be it any other thing. So you will have to evaluate using this equation, but then Fourier number is greater than point. What was our Fourier number? Our problem, what is the Fourier number? 3.07. So Fourier number is definitely greater than 0.2. Therefore, I can use the first term approximation. Remember, this equation is the same as the Heisler chart. Heisler chart used this equation for plotting. So this Heisler chart was obtained through this equation only. But in Heisler chart, the reading the chart and identifying the points that can result in errors. So if you use this equation, your error will be minimal. In fact, there won't be any error because this is an analytical solution. But then you will have to find zeta 1 and C1. So zeta 1 you will have to find using this equation. How to find this equation? Zeta n, the zeta 1 tan zeta 1 is equal to Biot number. What is our Biot number? 0.208. So zeta 1 tan zeta 1 is equal to 0.08. From that, you should have to find what is zeta 1. Substitute zeta 1 in this equation, you will get C1. Substitute this here, you will get the temperature distribution. Okay.
So,
Yes.
sir, in the heat transfer data book, so the Q naught is found out by rho CL Ti minus T infinity.
Ti, initial temperature minus T.
Yes, sir. Yes, sir. But in this one, sir, it is given just the length. But in this problem, we used it using volume. So, sir,
Yeah.
if we use length, sir, it becomes 25. So the total Q naught becomes half. So, sir, which one would be correct?
Is it the length which is given here?
Yes, sir. The half length given, so it will be 25 into 10 raised to power minus 3. But in volume, it will be 50 into
See.
10 raised to power minus 3.
Area, okay. No, actually, probably there's a mistake in this data book. I'll have to check and clarify. The data book
Alright.
contains mistakes, but the textbook is more authentic. Okay, I'll
Yes,
get back to you.
so
Textbook
we
is
use rho C V delta T.
yeah, 2L is what you have to use. Okay,
Thank you, sir.
I'll check and get back to you. Whenever this happens, you always rely on the standard textbook. Okay, when there is a difference between the equation in the data book and the textbook holds.
Okay, sir.
All right, so stop here and take your attendance.
Sir, how much error is acceptable?